Hello, we are Group 3 and our topic is cheese and searching. My name is Yuan Jiahui and my magic number is 204872. Every tree is a bipartite graph. A graph is bipartite if and only if it contains no cycles or odd lengths. Since a tree contains no cycles at all, it's bipartite. Every tree is a median graph. Every tree with only countably many vertices is a planar graph. Every connected graph G admits a spanning tree, which is a tree that contains every vertex of G and whose edges are edges of G. Every connected graph with only countably many vertices admits a normal spanning tree. Every finite tree with n vertices with n bigger than 1 has at least two terminal vertices. Its minimal number of leaves is characteristic of past graphs. The maximal number, n-1, is attained only by star graphs. The number of leaves is at least the maximal vertex degree. For any three vertices in a tree, the three paths between them have exactly one vertex in common. This vertex is called the median of these three vertices. Every tree has a center consisting of vertex or two adjacent vertices. The center is the middle vertex or middle two vertices in every longest path. Similarly, every n-vertex tree has a centroid consisting of one vertex or two adjacent vertices. In the first case, removal of the vertex splits the tree into subtrees of fewer than n divided by two vertices. In the second case, removal of the edge between the two centroid vertices splits the tree into two subtrees of exactly n divided by two vertices. Search trees. In computer science, a search tree is a tree data structure used for locating specific keys from within a set. In order for a tree to function as a search tree, the key for each node must be greater than any keys in subtrees on the left and less than any keys in subtrees on the right. For example, look at this graph. 8 is the bigger than any value in the left part, and 8 is smaller than any value in the right part, and minimum value in the right part is bigger than any value in the right. 9 is bigger than 8, 6, 4, 3, 7. Advantage of search trees. The advantage of search trees is their efficient search time given the tree is responsibly balanced, which is to say the leaves at either end are of comparable depths. Various search tree data structures exist, several of which also allow efficient insertion and deletion of elements, which operations then have to maintain tree balance. The purpose of search tree. Search trees are often used to implement an associative array. The search tree algorithm uses the key from the key value pair to find a location, and then the application stores the entire key value pair at the particular location. Spanning trees. In the mathematical field of graph theory, a spanning tree T of an undirected graph G is a subgraph that is a tree which includes all of the vertices of G, with the minimum possible number of edges. In general, a graph may have several spanning trees, but a graph that is not connected will not contain a spanning tree. If all of the edges of G are also edges of a spanning tree T of G, then G is a tree and is identical to T. Example of spanning trees. These 4 graphs are all spanning trees because they include all of the vertices A, B, C, D, and it's a minimum possible number of edges.
Now I will talk about the traveling salesman problem. Given a set of cities and distance between every pair of cities, the problem is to find the shortest possible route that visits every city exactly once and returns to the starting point. So, what is the difference between the Hamiltonian cycle and the traveling salesman problem? The Hamiltonian cycle is to find a tour that visits every city exactly once, but the traveling salesman problem is to find the minimum way to visit every city exactly once. Therefore, finding the minimum way of Hamiltonian cycle helps to solve the traveling salesman problem. There are lots of solutions for the traveling salesman problem. I have listed 3 of them at here. They are the naive approach or the brute force approach, the nearest neighbor method, and the approximate algorithm. Let us talk about the naive approach or the brute force approach. First, we consider a city as a starting and ending point. Then we calculate all the possible routes. Number of possible routes are calculated by permutation of n minus 1 divided by 2. Finally, we compare all the routes and find the minimum cost. Based on this graph, we can see that there are 6 routes in it, which is 12341, 12431, 14231, 14321, 13241, and 13421, which there are recurring routes in them. That 12341 is same as the 14321, 12431 is same as 13421, 14231 is same as 13241. So there are only 3 routes in this graph. So by comparing the cost of them, we can find that 80 is the minimum cost. Therefore, the minimum cost is 12431 or 13421. The next method is the nearest neighbor method. From this method, we always visit the nearest destination and go back to the first city after all cities are visited. So we set 1 as the initial and final point. Then we compare the 3 routes, which is to the 2, 10 distant, to the 4, 20 distant, and to the 3, 15 distant. So the 2, which is the 10 distant, is the least. So we go to the number 2. Next, we can choose from 4 and 3. So the distance to 4 is 25, and the distance to 3 is 35. So we pick 4, which is the less distant. Finally, we can only go to 3 because that's the last city left, and then we go back to 1. Therefore, the nearest neighbor method gives us the conclusion of 1, 2, 4, 3, 1, which is the minimum cost 80. The third method is to use the approximate algorithm. To solve the TSP using approximate algorithm, the problem needs to satisfy the triangle inequality. The triangle inequality states that the least distant path to reach a vertex J from I is always to reach J directly from I rather than passing through any other vertices. For example, distance ij is always less than or equal to distance ik plus distance kj. When the traveling salesman problem satisfies the triangle inequality, an approximate algorithm to solve the problem by using minimum spanning tree (MST) can be designed. First, we set 1 as our initial and final point. Then we construct a minimum spanning tree MST by using 1 as root using the Prim's algorithm. Then we list the vertices visited in the pre-order walk. The pre-order traversal of MST is 1, 2, 4, 3. Adding 1 at the end gives 1, 2, 4, 3, 1, which is the output of this algorithm. Now I will give a deeper explanation on this. First, we need to know what is full walk. A full walk is a list of all vertices when they are first visited in the pre-order. Vertices when they are returned after a subtree is visited in the pre-order is listed too. Therefore, the full walk for the graph should be 1, 2, 1, 4, 1, 3, 1. As the definition of MST says, it is a minimum cost tree that connects all vertices. The cost of best possible traveling salesman tour is never less than the cost of MST. In the pre-order walk, we replace 2 or more edges of full walk with a single edge. For example, 2, 1 and 1, 4 are replaced by 1 edge 2, 4. This will always be true when the graph follows the triangle inequality. Therefore, by replacing 1, 2, 1 and 1 4 with 2 4, and 4 1 and 1 3 with 4 3. We get the solve for the traveling salesman problem is 1 2 4 3 1.
Greetings, my name is Sarwin and I'll be talking about a tree analysis of sorting algorithm. Now, sorting algorithm is actually an algorithm which rearranges elements of a list in a certain order. You can notice in this picture here that this list here, the alphabets are not in an order. Through sorting algorithm, they become ordered. And few efficient and fast sorting algorithms are quicksort and merge sort. Okay, we have here a binary decision tree, and let's analyze this tree. It has 3 elements here, and we need to sort them. The height of this tree is 3 because the largest number of comparisons in the worst case scenario is 3, and the number of leaves, there are 6. The leaves here represents the number of possible orderings of the elements, and we can calculate this using the formula n factorial to get 6. And there are 5 internal vertices here. The internal vertices represents the comparison between 2 elements, and you notice that the tree here is balanced because all the leaves are at level 2 or level 3 starting from level 0, and the height can be calculated using the formula log to the base 2 n factorial with the ceiling function to give us 3, and it's equals because it's balanced, and the number of comparisons to sort 3 elements can be calculated using this formula omega 3 log 3, and the average number of comparisons to sort 3 elements will also be omega 3 log 3. Merge sort is a sorting algorithm which can be analyzed using a tree. Merge sort is actually a divide and conquer algorithm. The way this algorithm organizes the elements is by dividing the unsorted list into sublists, each comprising of one element here. After dividing, the merge sort algorithm will start to merge the elements. The first element of both lists is compared. If the sorting is in ascending order, the smaller element among the two will become the new element in the sorted list. And this will continue repeatedly until finally we have the elements here sorted in an ascending order. Next, heap sort is another sorting algorithm which can be analyzed using trees. All binary heaps are complete binary tree, and these trees store the items in a special order, either ascending or descending, depending on the type of heap, whether it's a maximum heap or a minimum heap. In a maximum heap, the value in the parent node is greater than the values in its children nodes. You can see here. In a max heap, the first step is to heapify each subtree from bottom up. You can see here the 12 is switched with number 1 over here at the top because 12 is more than 1, and this process will continue, and finally we will have a tree which satisfy the maximum heap property, that is the largest item is stored at the root node. After forming the maximum heap, the algorithm will then swap the root element and put it at the end of the array. You can see 12 is swapped with 9, and then after doing so, the 12 is removed, and the size of the heap is reduced by 1. You can see here that 12 is at the top already in the array, and after doing that, the algorithm will heapify again to have the highest element at the root. 10 is switched with 9, and the process repeats. Finally, we can see the elements sorted in an ascending order because it's a maximum heap. It will be the opposite for a minimum heap. And these are the ways we can analyze sorting algorithms using trees.
Hi, my name is Muhammad Zakaria bin Missouri. My metric number is 206386. So I will continue to prefix code, which is within the application of trees. So prefix code also known as prefix free code, and then purpose is to encode or compress data such that of all possible coding scheme, the best code will be the one with the minimum possible length. Symbol with higher probability of appearance will be assigned a shorter code than those with a lower probability. In this way, the average length is minimized. The code of one symbol cannot be the prefix of the code of any symbol. This is to avoid ambiguity in decoding. So if we imagine if leaf in a tree represents a symbol, any of its centers cannot represent any other symbol. So this is a figure for binary trees with prefix code. So the tree representing a code can be used to decode a bit string. So consider the word encoded by 111110 using the code in figure. This bit string can be decoded by starting at the root using the sequence of bits to form a path that stops when a leaf is reached. Each 0 bit takes the path down the edge leading to the left child of the last vertex in the path, and each 1 bit corresponds to the right child of this vertex. Consequently, the initial 1111 corresponds to the path starting at the root, going right 4 times, leading to a leaf in the graph that has S as its label, because the string 1111 is the code for S. Continuing with the 5th bit, we reach a leaf next after going right then left when the vertex labeled with A, which is encoded by 10, is visited. Starting with the 7th bit, we reach a leaf next after going right 3 times and then left when the vertex labeled with N, which is encoded by 1110, is visited. The last bit 0 leads to the leaf that is labeled with E. Therefore, the original word is same. Okay, we move on to Huffman coding. So here's the example in the figure. We using Huffman coding to encode a symbol with the frequency listed below. So as we can see here, the initial for us, and then for the step 1, we combine B and A with the smallest rate, and then step 2, we combine DC, and then we got here we combine EBA in step 3, and then go down straight, and then for step 5, we have complete trees, which is the 2 array. So games can be represented by tree also. They use tree to analyze certain type of games. Vertex represent the position can be in as it progresses. Edges represent legal move between this position. Games tree is finite if the game they represent never end. So here is the example. We using trees in a tic-tac-toe game. Some practical of tree and searching. Trees are extremely useful data structure with lots of practical of application. Following its few practical application. So first is binary search tree. I used to quickly check whether an element is present in a set or not. Heap is a kind of tree that is used for heap sort. A modified version of tree called trice is used in modern router to store routing information. Most popular database use B trees and T trees, which are variant of the tree structure we learned above to stroke their data. Compilers use a syntax tree to validate the syntax of every program you write. That's all from me. Thank you.